Alright, so today we will be doing some stereochemistry practice. This is a topic that a lot of students struggle with, and it's very important in your organic chemistry classes to be able to understand how stereochemical labeling works. So we're just going to be going through the stereosites that you would expect to see on your organic chemistry exams. So the three stereosites that we'll be discussing are chiral centers, E and Z alkenes, and cis and trans rings. And what we'll be doing is going through some practice problems and identifying which of the three are present, if there are multiple present, and then labeling them accordingly. So starting with this first example here, we have we have a carboxylic acid here. We have a 3-carbon chain with a methyl group attached over here and an alcohol over here. So thinking about these three elements, or I should say stereochemical elements that we can apply here, let's try to eliminate some. So cis and trans rings, there are no rings in the structure, therefore we can eliminate 3. I'll actually use red. E and Z alkenes. In this structure, we do have a double bond. However, that is not an alkene. Remember, an alkene is a double bond between 2 carbons. Therefore, there are no possible E and Z alkenes in this structure. And now we can move on to chiral centers. Now, if you remember, in order for a carbon to be considered chiral, it must be attached to 4 different things, quote unquote. So let's go to this carbon here. That carbon is not a chiral center because that carbon is sp2 because it has a double bond with oxygen. A chiral center, again, must be attached to 4 different things. Therefore, chiral centers are always sp3 carbons. So that carbon to the right is not a chiral center. Let's move to the carbon to the left over here. This carbon, you will also notice, is also not a chiral center because we have 2 hydrogens attached. And remember, in order for it to be chiral, it must have 4 different things attached. Therefore, we can eliminate that carbon as a chiral center as well. Moving on to this middle carbon. It looks like we do have 4 different things attached. We have a hydrogen, we have a methyl, we have a carboxylic acid, and we have a CH2OH. So we have the carbon here, the 2 hydrogens, and an alcohol. That being said, we can consider this carbon to be chiral. And now we can go about labeling it as R or S. And we do that using the atomic number of what's attached to that carbon. So we know hydrogen has the lowest atomic number of all the elements. Therefore, we can rank that as 4. Now, you'll notice we have 3 separate carbons attached to this chiral carbon. Therefore, we'll have to look what's beyond that carbon to see what will take priority. Moving to the right over here, this carbon is attached to oxygen. It's actually double bonded to oxygen. Therefore, we can consider it as it's attached to 2 oxygens on top of another oxygen in that alcohol. So in this case, to the right, we can consider it to be like this. Although this is not really possible, that's how you can kind of consider it. If it's double bonded to an oxygen, you can consider that carbon to be almost bonded twice separately to oxygens. This carbon to the left, we see is bonded to 2 hydrogens and 1 oxygen. So immediately we know that this carbon to the right is going to take priority. So if we cancel out this oxygen and this oxygen, we're left with 2 hydrogens and 2 oxygens. Oxygen has a larger atomic number, therefore this carbon to the right, will come before the carbon to the left. And now let's move on to this methyl group. There are no oxygens attached. It's a simple methyl with 3 hydrogens attached. Therefore, we know that this methyl group is going to be ranked 3. This carbon to the left is going to be ranked 2. And this carbon to the right is going to be ranked 1. Now we can go about labeling it R or S. Remember from your organic chemistry classes that R means that the direction in which 1, 2, and 3 are oriented is counterclockwise, and S is clockwise. So if I do this, we know R is counterclockwise and S is clockwise. And so the strategy here is to put 4 in the back of our point of view. And we want to trace the flow of 1, 2, and 3. And we do this by using a Newman projection. You know, some teachers and maybe your peers will tell you to use the your right hand and your left hand and point the thumb in the direction of the 4th ranked attachment, and use your fingers to curl in that direction. I personally don't think that's a reliable method. I think that's very hard to understand, and there's so many anomalies that I think using a Newman projection is very important, and I think it's definitely more reliable. So if we want to put this 4th priority hydrogen in the back, and we see that it's on a wedge, so this is going to be a little more difficult. So we kind of have to consider the point of view as we are looking from the back of this screen right here. So if we draw a Newman projection, we would see 2 coming down and 1 coming up. Now, and this is if we looked at it from the back. It's kind of hard to draw, but I hope you're able to visualize what I'm trying to explain right now. So when looking at this molecule from the backside with that hydrogen now pointed in the back, we can kind of consider it as you're no longer able to see that hydrogen. You will notice that 1 will now be on the left, 2 will be on the right. When I mean 1 and 2, I mean the rankings that I put on the attachments, and 3 will be sticking straight up. Now we can trace 1, 2, 3. We see that that is the counterclockwise direction, therefore we can rank this as in our chiral center. And that's how we would label this molecule when doing IUPAC labeling. We would first label it as an R, a molecule with an R chiral center. Moving on to the next example, we have a similar molecule from the first one. So if I do 1, 2, and 3, remember 1 is the chiral center, 2 is the E and Z alkenes, and 3 is the cis and trans rings. I'm sure you've already done by now. You can eliminate 2 and 3 from this example. There are no rings in the structure and there are no alkenes. So we're now, again, stuck with the possibility of chiral centers. When looking at this structure, you should be able to notice that, yes, I do have 2 chiral centers in this molecule. One right here and one right here. You know, this carbon to the left, we have a sulfur attached, a methyl group attached, a hydrogen attached, and a carbon with multiple different things attached. And the same can be said about the other carbon. We have a methyl group attached, and a nitrogen attached, a carbon that is double bonded to an oxygen and bonded to a sulfur, which is also known as an ester, or a thioester, I should say. And again, this carbon to the right is bonded to that carbon to the left, which is bonded to a sulfur, methyl, hydrogen. So we can consider this carbon to be different from this carbon when ranking this center. And when ranking this center, we can consider this carbon to be different from this carbon. So now let's go about doing that. So if I do it in blue here, let's start on the left carbon. Hydrogen, it's always going to be 4, has the lowest atomic number. Sulfur is the molecule with the highest atomic number in this entire molecule. So we're going to label that as 1. Now we have a methyl group. So if I put H3C, and we have this carbon right here, that other chiral center. Now, looking at this, the carbon to the right, that carbon is attached to a nitrogen, and two other carbons. This carbon is only attached to 3 hydrogens. So carbon and carbon, that's going to cancel out. We can't prioritize anything there. However, if we move one atom, I should say, forward, we see that we run into a nitrogen or 2 different carbons. If we go from this carbon to the next atom, we see that there is a hydrogen only. Therefore, this carbon will be ranked as 3, and this carbon will be ranked as 4. Sorry, my mistake. This carbon will be ranked as 2, and this carbon will be ranked as 3. Now we can go about figuring out the actual label for it. Again, we want to put this 4th priority atom in the back. Therefore, we're going to draw a Newman projection with our eye coming from that direction. Because when we're looking at it from this direction, this hydrogen is now in the back out of our sight. Therefore, we can then trace the flow of the 1, 2, and 3 ranked attachments. So if I'm looking at it from this point of view, I'll notice that 2 is facing down, and 3 is sticking out right at us, so 3 will be on the left, and 1 is into the page, so 1 will be on the right. And if we trace the flow, we see that is in the clockwise direction. Therefore, we can consider this as S. Now, I'd like you to practice this on your own, and hopefully you will get this chiral center labeled in red as R. Okay. Moving on to the next example. Again, 1, 2, 3. So, in this case, we do have an alkene. Therefore, 2 is applicable here. We have a benzene ring. However, that is not a cis and trans ring. A cis and trans ring must have sp3 carbons. These are sp2 carbons. Therefore, this cannot be applied here. So we can eliminate a cis and trans ring. And anytime you have a benzene ring, you should not think of chirality with respect to that direct benzene ring. Maybe something coming off of the benzene ring can be chiral, but an actual benzene ring is achiral because all the carbons are sp2. And remember, for it to be chiral, it must be sp3. Now, chiral centers, that is also a possibility here, as we do have a sp3 carbon with it looks to be 4 different things attached to it. So 1 is also applicable here. And we'll do the chiral center stuff in red, and we'll do the cis and trans ring in blue. So we've already gone through chiral centers just now, so I will be doing this just very quickly. Chlorine, we know, is going to be 1. Nitrogen, 2. The carbon, that's 3. Hydrogen, as always, is 4. We want to put that 4th priority group in the back. Let's draw a Newman projection. So we want to look at it. I apologize for the terrible eye. If we want to look at it from this direction, you'll see 3 is going to be sticking straight up. Chlorine is sticking right out at us, so from this point of view, chlorine will be 1 on the right, and this NH3 will be on the left, so 2. And if we draw this, we see that is clockwise, so this is going to be S. Moving on to the E and Z alkenes, we see that we have a double bond between this carbon and this carbon over here. And the way you rank E and Z alkenes is E equals opposites. It's kind of a neat way you can think about it. Meaning, the higher ranked priorities from each side of the alkene are on the same side of the alkene. And I'll get into that in a second. Sorry, opposite sides of the alkene. Z would be same side. And this is where the two higher priority rankings would be on the same side of the alkene. E means that they're on opposite sides. So what you're going to want to do is basically split a line between the alkene and just consider each side separately. So if we look at this carbon here, we have oxygen attached and a carbon attached. Oxygen has a larger atomic number, so we're going to label this oxygen 1 and this carbon of the benzene ring 2. We have a methyl group for this carbon, a methyl group attached, and another carbon attached, but this carbon is attached to a nitrogen and a chlorine and a hydrogen. So the two carbons, they're going to be the same, so we can go to the next atom over. The next atom over for this carbon over here is simply 3 hydrogens. The next atom over for this carbon over here is either a chlorine, a nitrogen, or hydrogen. Basically, if you're between, you might be thinking, oh, why wouldn't I just go straight to the hydrogen? Why do I have to go to the chlorine or the nitrogen, allowing this carbon to take priority? You basically want to choose the pathway that lets your carbon that you're working with win. In this case, with this carbon on the bottom, we're going to assume the pathway that we're looking at in order to rank based on atomic number, we're going to go towards the higher atomic numbers. So with this carbon, although we have 3 things attached, I'm going to go directly to that chlorine, which has a pretty high atomic number. So this carbon is going to be labeled 1, and this methyl group with this carbon is going to be labeled 2. So we have 1, 2, 1, 2. You'll notice that 1 and 1, which are the 2 higher ranked groups, are on opposite sides. Therefore, we label this alkene as an E alkene. And that's basically how you go about doing it. So in this molecule, we have an E alkene as well as an S chiral center. Final example that we will be going through, you'll notice kind of has some elements that we haven't really discussed yet in previous problems. We do have a ring with sp3 carbons, therefore we can consider cis and trans rings. And remember, cis and trans rings are also achiral, because in order for something to be chiral, you have to have 4 different things attached to a carbon. So if we look at this carbon over here and this carbon over here, we see a line of symmetry drawn. There is a methyl group, a hydrogen that you could draw in, I suppose. Same with this side. And if you go down this pathway, you'll notice it's the exact same as if you go down this pathway. Therefore, both of these carbons are achiral. And, if you drew the pathway like this way, you went like this, it would obviously be symmetrical. Therefore, we can consider cis and trans rings here. E and Z alkenes, we do see 2 alkenes in this scenario. We can consider that. Are there any chiral centers? Well, let's look at the sp3 carbons. This carbon is not chiral because we have 2 hydrogens attached. Same with this carbon. This carbon is not, actually, these 2 carbons, I'll label that in red, are chiral centers. However, for the sake of this problem, we will not be labeling those chiral centers. I just want to focus on the cis and trans rings as well as the E and Z alkenes. But feel free to do that for your own practice. Although it may be difficult, considering I did not put in the dash and wedge for this problem. And on your organic chemistry exams, in order for you to label a chiral center, it is imperative that you know what the dash and wedge attachments would be, and that would be given to you in the problem. So let's just disregard the chiral centers for the sake of this example. So let's do the E and Z alkenes in blue, and let's do green for the cis and trans rings. So cis and trans rings, we can almost apply the same rule as the E and Z alkenes from the previous problem. Let's split this ring in half, and we have a cis ring when first priority groups are on the same side of the ring, and we have trans when first priority groups are on opposite sides of the ring. And when I mean same and opposite sides, I mean they're facing the same side. So two things that are on dashes on opposite sides of the ring are going to be on the same side. They're going to be facing into the screen. And two things that are on wedges are both going to be pointing straight up out of the page on the same side of the ring as well. But something on a dash and something on a wedge are going to be pointing in opposite directions and on opposite sides of the ring. In this case, we have carbon and hydrogen attached to this carbon. And same over here, carbon, hydrogen. Carbon obviously has a higher atomic number than hydrogen, so we'll do this 1, 2, and the same thing can be applied. 1, 2. And we see that the 1 priority groups, which are the 2 methyl groups, one's on a wedge and one's on a dash. Therefore, we can consider this ring to be a trans ring. Now let's move on to the alkenes. Same thing. Let's split this alkene in half. We have 1, because oxygen has a higher atomic number than hydrogen, 2. This is obviously going to be a 2, and this carbon is going to be a 1. We see 1s are on opposite sides, so that's going to be an E alkene, opposite, remember. We have an alcohol here, oxygen, that's going to be 1, hydrogen is going to be 2, carbon is going to be 1, hydrogen is going to be 2. This is also an E alkene. And I did this symmetry on purpose. The 2 alkenes are going to be the same in order to show what the requirements of a cis and trans ring. It must be achiral. Whenever you have if this carbon were somehow chiral, or this carbon were somehow chiral, you can no longer consider it to be a cis and trans ring. It must be a ring that is achiral in order for it to be considered cis or trans. So that concludes our lesson on stereochemistry practice. I'll have my email in the description if you'd like to email me any problems that you would like for me to discuss. I'd be happy to go through them in future videos. If you have any suggestions on what topics you would like for me to cover in organic chemistry or even biology or biochemistry, I'd love to interact with all of you and see what the demand is. Hope this helps, and good luck with your classes in organic chemistry.